You know that on the Euclidean plane, in every triangle, the sum of the angles is equal to 180 degrees. In fact, as written here, if you give yourselves three angles, each of them, of course, positive angle, and their sum is equal to 180, then there exists a triangle on the Euclidean plane that has exactly these angles. So it's an if and only if statement. So, in other words, on the Euclidean plane, three angles are the angles of a triangle if and only if their sum equals to pi. Now, you've already seen that that's not the case on the hyperbolic plane. Namely, you've seen examples of triangles where the sum of the angles was less than 180. But not only you can have triangles whose sum of the angles is less than 180, in fact, something much more extreme is true. Namely, the following theorem. So let alpha, beta, and gamma be, again, positive angles on the hyperbolic plane, whose sum is less than 180, so less than pi. Then there exists a hyperbolic triangle that has these angles as its angles. So that's quite an extreme case. On the Euclidean plane, only 180 will give you a triangle. That is, if you give yourself three angles, if they add up to anything other than 180, you're not going to have a triangle. On the hyperbolic plane, if you give yourself three angles that add up to 30 degrees, 45, 90, 88, 120, doesn't matter. As long as the sum is less than 180, there is a triangle that has these angles as its angles. So let's prove this theorem. So I'm going to give myself three angles. So proof. So let alpha, beta, gamma be hyperbolic angles such that their sum is less than pi. So what I'm going to do is that we're going to construct a triangle that has alpha, beta, and gamma as its angles. So we will construct a hyperbolic triangle with angles alpha, beta, and gamma. First note that because the sum of the angles is less than 180, then at least one of the angles must be less than 90 degrees. So I'm going to assume without loss of generality that alpha is less than 90. So we can assume without loss of generality that alpha is less than pi halves. Okay, now here is the hyperbolic plane, and I marked on it the point 0, 0, 1. So now I'm going to choose a point D on the x-axis such that the angle ADO, so here's O, is equal to alpha. So this angle here will be alpha. Okay, let's write this down in words. So, so let D on the hyperbolic plane, and we'll just denote its coordinates. That's actually not on the hyperbolic plane, I'm sorry, it lies on the x-axis, so it is not on the hyperbolic plane. So D equal to D comma 0 be the point on the x-axis such that the Euclidean angle ODA is equal to alpha. right? So if you give yourself this point, by moving the point D along the x-axis, you can get any angle you want. So you can get the angle alpha. Okay, now we're going to mark another point, and namely something that would give us a point, the angle beta. So here, somewhere on this orange arc, which we're actually going to call G. So let's give it a name. So let G be the bout geodesic. On H, that is the Euclidean circle. Centered at D. Of radius AD. Okay, so this orange arc here, that's the geodesic G. Name here. Okay. So now let E, and I will only care about the x-coordinate of this point, so I'm going to write E, comma, dot. So the dot is just some number, it's the y-coordinate of the point E, but I somehow don't care about the y-coordinate, so I'm not going to introduce another letter into the notation. So let E be the point on G, so on this arc, such that the angle between the x-axis and DE is beta. So here, somewhere here is the point E. Its coordinates are E, comma, dot. So I connect it. And here's the angle beta. I want you to note that this is always possible, because the sum of the angles alpha and beta and gamma is less than pi. So in particular, the sum of the angles alpha and beta is less than pi. Alpha took up this angle, so for the point E, I have the entire space here from this point to this point, so that means that angle that this ray forms with the x-axis can vary between 0 and pi minus alpha. And because alpha plus beta is less than pi, I know that beta is certainly less than pi minus alpha. So that means there's definitely, no matter what beta is, there is such an E here on this geodesic G. Okay, so I've got these two, and now let's actually draw some vertical lines here. So I'll connect this, I'm going to draw a vertical geodesic here. So I'm going to call this M. I probably don't want to go too high, so I actually have space to write something. So just like that. M. So let M be the vertical geodesic segment above E. Okay, and we had this this theorem before that tells us that the angles between geodesics can actually be represented by the angles between rays originating from the x-axis. And in fact, this angle here between the geodesic G and the y-axis is therefore alpha. And this angle here is the same as the angle beta. Maybe just quickly why that is the case. Because this angle alpha, remember I drew it like this, but by definition it's not really the angle that extends all the way from the y-axis to the arc. It is the angle between the y-axis. I'm going to draw a little picture here. Between the y-axis, and here is the geodesic G. So it's the angle between the y-axis and the tangent line to this arc. And I know that this is actually an arc of a circle, so the radius forms a right angle with the tangent. So that means, in fact, that this angle here, alpha, is equal to this angle, alpha. Okay? Just a simple exercise, but if you look at the previous video, I actually proved this fact. So then the same thing is happening here, right? The angle beta is not really the angle between the curve and the M. It's the angle between this line M and the line that is tangent to the curve. And the line that is tangent to the curve is perpendicular to the radius. So if you look at this angle is actually equal to that angle. Again, I should draw a tangent line here, but I don't want to draw too much on this picture. Okay, so there we have it. Well, this doesn't give me a triangle, right? Because I have some angle alpha here, some angle beta here. So I need to do a little bit more work to actually get a triangle. So maybe let me just put this in words, what I just wrote down here. So then we get that the angle between the geodesic G and the y-axis is equal to alpha, and the angle between the geodesic G, or the line M, and the geodesic G is beta. Okay, so that's what I just marked here on the picture. Fine, now we're going to mark another point, and that's going to be a point anywhere between A and E. So maybe I'll use the black color. So let B here. So that's going to be B. And I will only care about its x coordinate. So I'm again going to write it as B comma dot. I'm going to introduce a point like this and another vertical geodesic above the point B. So let B denote an arbitrary point on the arc AE. Okay, so that's just any point between A and E on this arc, on the arc AE, and let N be the vertical geodesic segment above B. Okay, I'm going to now denote the angle, so set theta of B to be the angle between G, between N and G. Why do, so where is it on the pictures here? I maybe just draw it small. Theta of B. Why do I write this theta of B? Because so the point B is arbitrary here, so that means I could actually move it around if I wanted to, and then this angle theta is of course going to change. So as I move it from this point, in fact, you know, so the smallest, so because the point B lies between A and E, if I move this all the way to E, then the theta of B would be equal to beta, and if I move it all the way to the other side, then the angle that I get will be pi minus alpha. So that's sort of that's the range of theta B. So note theta B is between beta and pi minus alpha. And in fact, note another thing, as I move the point to the right, this angle becomes smaller, right? This is the angle, but if I keep moving it to the right, then this angle decreases to beta. Beta is like the smallest it can ever get. On the other hand, if I go in the other direction, then it increases, like around here, this angle will be the right angle, and then if I keep going, I eventually get the angle to be pi minus alpha. So that means if I move the point to the right, the angle decreases. If I move it to the left, the angle increases. And if I move the point to the right, then the x-coordinate, little b, increases. So as the x-coordinate increases, the angle decreases. So let's write this down. So we note that theta of B is a monotone decreasing function of B. So that means as little b increases, so the x-coordinate increases, the angle decreases. Where actually is that angle on the picture here? Well, again, the same rule applies as before, and if I connect this with the point D, then the angle theta of B is this entire angle here. That is equal to the angle theta of B. Okay. What's the what am I getting at with this? So there exists a bound geodesic, and I'm going to call this geodesic H of B, that joins the point B with the y-axis, and such that the angle between this geodesic H of B and the geodesic G is equal to beta. All right, so let's see how this goes. So I know that this angle, let's actually maybe let me just say here that it's not only monotone decreasing, but it's actually continuous monotone decreasing function. Continuous. So this angle, right, it changes between beta and pi minus alpha, so it's always greater than beta. So that means I can always cut a bit of this angle to get beta. So essentially that's what I'm going to do. I'm cutting some part of this angle to get beta. Okay, just going to mark it like this. So the angle between the orange and this red part here would be beta. And then I'm drawing a geodesic. So again, it's about geodesic. So like part of a circle. And I claim that it intersects the y-axis somewhere. Well, it has to intersect the y-axis somewhere because I know that this has to be a circle. In fact, it's probably the curvature doesn't look correct here. It should be maybe less curved somewhat. Okay, maybe that's better. I know that the geodesics are always circles. The bow geodesics are arcs of circles that are centered and somewhere on the x-axis. So it has to come down to the x-axis eventually, right? If it were to come down before it hits the y-axis, then it would have to intersect this geodesic here. But that's not the case, right? Because the angle here is actually bigger. So it has to cross the y-axis somewhere. So I'm going to call this point of intersection here C of B. So this is C of B. So its coordinates are 0 and little c of B. So let's write this down. So let C of B be, whose coordinates are 0, C of B, be the point of intersection of, so this here, right, this is H of B, of H of B with the y-axis. Okay, so here I'm going to write that this is the angle beta here. That's how I chose it, right? The angle between H of B and G was supposed to be beta. Again, just to remind you, this is not really the angle between these curves. It's the angle between tangent lines, but let's just leave it like this. Okay, so that's already looking good because that looks like a triangle now. Right? That looks like a triangle. So there's another angle here. So I'm going to denote this last angle here by gamma of B. Right? You see, it all depends on this point B. Right? If I move this point B, everything changes here. The black line moves to the right. The angle theta of B becomes bigger. So the geodesic sort of starts earlier and probably hits the y-axis at another point. So far we still have this one degree of freedom. Maybe we can change this point B. Okay, so let's just define this gamma. So let gamma of B be the counterclockwise angle between the y-axis and H of B. I don't really care for the orientation of the angle. I just mean that it's not this angle, but that it's that angle over here. Okay. We have that gamma of B is a continuous function of B, and what's the range? With range between 0 and pi minus alpha. Yeah, so if you move this point very far to the right, here to the point E, then you see that the red geodesic almost follows the orange one. This is just slightly above it, just slightly above it. Which means that the point of intersection here, this point would actually be very close to that point over here. And this geodesic, the red geodesic, will almost be like parallel to the orange one. So this angle will be very close to alpha. A little more, but sorry, it will be close to pi minus alpha, right? It's complementary, it's supplementary to alpha. Because it will be this, so maybe just a little picture here. If this is alpha, right? And so the other geodesic, if it went very close, it would be here. So that would be the angle. So you see, they're almost, so it will be close to pi minus alpha. The angle between this tangent line and the y-axis. On the other hand, if I move this point closer to this side, you see that that angle actually becomes smaller. Right, so I'm not going to draw the picture anymore. But if you move this point over here, draw the picture for yourself, and you will see that the angle gamma of beta is actually small. Okay, so it's a continuous function with this range. So continuous function with a certain range achieves every point inside this range. So we get, so for some value of b, by the intermediate value theorem, so for some value of b, we get gamma of b equal to gamma, the third angle that we want, right? So note that the angle gamma is also in the same range. It's certainly in the same range because the sum of the three angles is less than pi, so each of the angle beta and gamma both have to be less than pi minus alpha. Okay, so I have my triangle: alpha, beta, gamma, if I choose the value of the parameter b correctly, right? So the triangle is A, B, C of b for that particular value of b that gives you angle gamma.